So continuing on equilibrium. And so we're going to take and we're going to use our equilibrium values, and we're going to look at the equations that we have involved, our expressions, and we're also going to consider our initial values, because not only do we want to know what to do with reaction at equilibrium, we need to know if it is at equilibrium. So we're going to have to do some calculations on that as well. First of all, if we would like, we can relate K sub C to Kp, our equilibrium constant in terms of our concentrations versus our equilibrium constant in terms of partial pressures. How can we do this? Well, note if this only works if we have all gases. If we have all gases, then we're going to be able to compare our concentrations versus our pressures. And if we have all gases, we know that we have PV is equal to nRT, which tells us our pressure is equal to N over V, which is moles per liter, which is concentration, multiplied by RT. So our K sub P's depend on our molarity and some RT value. So if we have some generic reaction again, our K sub P is going to equal our K sub C multiplied by RT to the delta N, where delta N is going to be moles of gas of products minus the total moles of the gas that are reactants. So we can plug that in and do some math. So let's say that we have this reaction right here. So the first thing we're going to do is we're going to write our equilibrium expression. And I'm going to start with the K sub C because I am given concentrations. And I know my expression tells me that K sub C is equal to the concentration of the product, COCl2, divided by the concentration of the reactant, CO, multiplied by Cl2. This is all one-to-one, so each of these are raised to the first power. Now, at equilibrium, and these are equilibrium values, we can plug in our concentrations. And if we do that, this is going to be 0.14 divided by our CO is 0.02, excuse me, divided by 0.054. If we do the math here, we're going to discover that our K sub C has a numerical value of 220. We have two sig figs, so 220. Now we can relate Kc to Kp because Kp, our equilibrium constant, just in units of atmospheres rather than molarity, is equal to Kc, this value right here, multiplied by RT to the delta N. Delta N is going to be moles of the product minus moles of the reactant. And again, this is only going to work for gases. So this is going to equal 220 multiplied by R. Well, because this is PV equals nRT, this is 0.08206. The units would be liters, atmospheres per mole Kelvin. We leave the units off. I know that's sloppy. Over the temperature in Kelvin, that's 74 plus 273. And it's going to be delta N. Well, delta N is moles of the product, which is 1, minus moles of the reactant, which is 2. So this is going to equal to the minus 1. And when we finish our math here and we get K sub P is going to equal a value of 7.7. We can also manipulate, or we can mess with K. And we can mess with K, first of all, by taking and flipping it. If we take a look at this reaction where we have N2O4 goes into two NO2s, and we get a K value, so we've been given equilibrium concentrations, and we realize this value is small. And if this value is small, inherently, we're going to have, according to this reaction, more N2O4 than we have NO2s. If we take and reverse the reaction, if we reverse the reaction, instead of having two NO2s on the numerator, we're going to have two NO2s on the denominator. And our K reverse is going to equal the concentration of N2O4 divided by the concentration of NO squared. Well, if we take a look and we compare these two, we realize that if we reverse the reaction, we are going to do the mathematical inverse or the reciprocal of the original. So K for the reverse reaction is equal to 1 over K for the forward reaction. So in this case, if we plug in and do the math, we're going to reverse it or inverse it, and we're going to get that the new K is equal to a value of 216. Just taking 1 over 4.63 times 10 to the minus 3. All right, so that would be if we reverse it. Well, what if instead of doing that, we take our original reaction right here and we multiply by 3? So if we take our N2O4 goes into equilibrium to 2 NO2s, such that our K, and let's just call this reaction 1, or reaction 1 is equal to NO2 squared over N2O4. And we take this equation and we multiply this entire thing through by a 3. Well, if we multiply this through by a 3, we are now going to get K for this reaction here, which I'll call K3, is equal to this entire reaction right here raised to the third power, because it's going to equal NO2 now to the 6, which is 2 cubed, divided by N2O4 cubed. What does this mean? It means our K for our new value, or our K for reaction number 3, is going to equal our K that's old, 4.63 times 10 to the minus 3, and we're going to cube it. So if you take and you multiply any reaction that you have by some value n, so let's say you have a balanced reaction, and you multiply it through by some value n, you're going to take your K and you're going to raise it to the same n. So if you multiply through by n, your K new will equal K old raised to the n. So in this case, you can simply do the math, and you're going to get K new is equal to 9.93 times 10 to the minus 8. Now, if you have a multi-step reaction where you make a product and then you use the product again, you are going to discover that you, in fact, can go straight from the reactants to your new set of products, and you will simply multiply the Ks. We will see that in the following chapter. All right, so let's look at initial amounts. If we look at initial amounts, we can figure out if our reaction is equilibrium. So let's say, for the example, that we have our N2O4, and it is decomposing to make 2 NO2s, and that at some temperature for this, our K sub C is equal to 1 over 200, meaning we have 200 reactants for every one product. Well, let's say that we start here with all reactants. So let's say we start with all reactants and no products. Well, if we start all reactants and no products, it tells that our ratio initially is going to be 0. So our ratio initially, and our ratio initially is Q, is going to be reactants and no products, so it's going to be 0 over some number of reactants, and our Q here is going to equal 0, and if our Q is 0, our Q is going to be less than K, meaning we do not have enough products. So if we look at it and we realize that our Q is smaller than it needs to be, it means we don't have enough products, and the reaction is going to shift to make products, which makes perfect sense, because if I haven't got any of this, my reaction is going to make some. But let's say instead I have lots of products, and I take a look at this reaction, and I have, for example, 1,000 products and 1 reactant. Well, if I have 1,000 products and 1 reactant, this reaction is not at equilibrium. Equilibrium exists in this reaction when we have 1 product for every 200 reactants. So in this case, and I look at this, my Q is going to be bigger than my K. My ratio of products to reactants is going to be too big, and the reaction will shift to the left. All right, so let's look at this reaction here. We just reversed it, and we've got a K for this. And we say that here our K, which has a value of 171, at this temperature is going to equal the concentration of N2O4 over the concentration of NO2 squared. It says that the ratio of the products over the reactants is going to equal this value. Now the question is, if instead of being, and this is at equilibrium, this is where it has allowed to react until the rate forward is equal to the rate reverse. So if instead I mix together some initial amounts, now if I mix together initial amounts, I'm going to get a Q. Q is just a ratio, it means quotient. So this is my ratio initial. And my ratio initial is going to be the amount of N2O4, which is 0.025, divided by the amount of NO2, which is 0.015, and this quantity is squared. So if I take and I do the math on this, I get a value of 111. So if I look at this, I can see that my Q is less than K. That my ratio initial is smaller than my equilibrium concentrations. And this tells me that I have too few products. This needs to react until the ratio of the products to the reactions is 171 to 1, and now I have 111 to 1. And because Q is less than K and I have too few products, the system is not at equilibrium, and we say it is going to shift to the right, which means the NO2 is going to react to make more N2O4. So what is the takeaway? The takeaway here is that, let's say we have this reaction right here where carbon monoxide reacts with water to make carbon dioxide and hydrogen. And we have some ratios. And in mixture number 1, we have carbon monoxide and water. Mixture number 2, we have carbon dioxide and hydrogen. Mixture number 3, we've got carbon dioxide and water and a little bit both of carbon dioxide and hydrogen. So what? Well, what it says at the end is that it is going to shift and reach equilibrium. It is going to shift and reach equilibrium such that the ratios are going to equal the equilibrium constant no matter where you start from. So clearly, if I start out with smaller amounts of the CO and H2O, in this case, mixture number 1, I'm not going to make as much stuff as I do in mixture number 2, but the value of the products over the reactants is going to be the same. The value of the products over the reactants at equilibrium is going to react until I get 0.640 to 1, no matter where the starting point is. So if Q, the ratio initial, is less than K, it tells me that I do not have enough products and the reaction is going to shift to the right. If the Q is greater than K, then it tells me that I have too many products and I'm going to shift to reactants. And when Q equals K, I am at equilibrium.